Hello and welcome. In this video, we will walk through a demonstrator developed by Teledyne E2V and CEA-Leti. This demonstrator is designed to evaluate how non-uniform sampling can help reduce data throughput in high-speed ADC systems. This is particularly relevant for applications like radar, electronic warfare, and satellite communications, where data volume and power consumption are major constraints. First, what is non-uniform sampling? In systems using high-speed ADCs like EV10AS940, which sampling at 12.8 gigasamples per second, the resulting data rate can be extremely high. This creates challenges in data transfer, storage, and real-time processing. Non-uniform sampling uses the mean sampling rate reduction by skipping the samples at random time position. Although there is a loss of output SNR, the information for the signal detection, its identification and demodulation is preserved. Now, what are the elements of the demonstrator? The demonstrator is composed of three elements: the EV10AS940 ADC board, capable of sampling at 12.8 gigasamples per second with 10-bit resolution; the ZCU111 board, which hosts the FPGA cores for ADC testing, DVB-S2 detection, and partial demodulation. The host PC manages the demonstrator's configuration, handles parts of the data processing from the FPGA, and provides real-time visualization of the results. The ADC streams data to the FPGA via high-speed serial links over EasyStream protocol, while control and data retrieval are managed through TCP/IP communication between the PC and the FPGA board. What does a practical NUS-enabled acquisition system look like in action? The RF input signal is generated using a Rohde Schwarz SMM100A for the DVB-S2 signal here at 28.685 GHz. The evaluation was made combining this signal and the noise pattern. Today, the demonstration is done without the noise generator. The FPGA performed detection using FFT-based channelization, proceeding by windowing to improve spectral resolution. The GUI allows users to configure parameters such as FFT size, compression ratio, window type, and detection threshold. Detection is based on accumulated FFT power compared to calibrated noise reference. Can we reliably demodulate signals even when sampling is sparse and noisy? Once a DVB-S2 signal is detected, it is demodulated through a hybrid pipeline. The FPGA performs random non-uniform sampling on the input signal, frequency down conversion, low-pass filtering, and decimation, reducing the data rate from 12.8 gigasamples to 100 megasamples per second. The PC handles the remaining steps: ultra-fine frequency correction, RRC filtering, frame and sample synchronization, equalization, and the BER EVM estimation. The result is a clean constellation diagram and zero BER under ideal condition, confirming the integrity of the signal after NUS-based acquisition. An example here of transmission in the fifth Nyquist zone of a DVB-S2 32 APSK signal at 28.6 GHz from Rohde Schwarz instrument without noise. The compression ratio equal 1. We observed an EVM between 1% and 2%. There seems to be a small amount of phase noise. We can modify the compression ratio to 2 and to 4. And we see that the signal is correctly decoded. Another example done with noise pattern showing that in low SNR conditions it is possible to decode correctly the binary stream. As a conclusion, our results show that non-uniform sampling enables robust detection and demodulation even at low SNRs. It's a practical way to reduce data rates and power consumption while maintaining signal fidelity. This demonstrator provides a concrete example of how non-uniform sampling can be applied in ADC systems and open the door to future ADCs usage. If you have questions or if you are interested on the EV10AS940 and non-uniform sampling, please contact us using Teledyne E2V Hotmail address. Thanks for watching.